Well, good afternoon, everybody, and thank you all for coming on such a beautiful afternoon. It's a great honor and privilege to give this talk, and it's a rather personal talk. What I'm going to do is talk a little bit about my own history and background, and then consider what we need for the future in terms of how we think and approach the world in these very difficult and changing times. I guess one of my messages is going to be how important science and rational thinking is for society and humanity, and what the threats to that process are, and how we might approach those difficulties. So this is a sort of timeline of my life. You can see the red bit, and that's Singapore. So I came to Singapore in 2004. So I originally came for 2 years of sabbatical leave, but somehow the Singapore effect took over, and I've stayed here ever since. I was born in 1952. I was a very poor student at school. I got into grammar school but I didn't do very well at school. And my kind of intellectual awakening happened when I went to University College London. I managed to get into that wonderful university, and that was really like an electric shock for my system, and kind of woke me up. And after that, things have gone very well. So I've had a rather wonderful life, actually. I was successful in my undergraduate degree. I did a PhD with a wonderful man. I'll talk about it a bit more in the future. And then my first period as a scientist, as a postdoctoral scientist, I made this discovery of P53. At the time, we didn't fully appreciate how important it was, but nevertheless, I've worked on it ever since. So essentially, I've worked on one protein for all of my life, and it's been absolutely fascinating. And as you heard in the introduction, it's obviously important because it's altered in most human cancers. And so I went through this process of the academic process, which most scientists go through. That is, you do a couple of periods of training after your PhD. I did one of those periods in the United States in Cold Spring Harbor, where Jim Watson was then the director. He was the man who discovered the structure of DNA, along with Francis Crick. And then I became independent and had my own laboratory and started to teach and train my own students at Imperial College, and later in a research institute in the ICRF. And during that time, I wrote a book, a technology manual, which I remember when I was writing it, the people who encouraged me to write it said, "Oh, we might sell as many as 1,000 copies, David." And 50,000 copies later, we realized that actually we'd found out something very important, is that this kind of technical information is very useful to scientists to understand how to do their work. I guess the next sort of big event is I started a biotechnology company. I became a bit frustrated with the pace of translation. So when you're doing science and you make a discovery, you want that to be turned into something useful, and you have to partner industry to do that. And one way to approach that is to start a company. And so I started a company in Dundee called Cyclocell. It's still on NASDAQ. I don't advise any of you to invest in it. It's probably the least successful biotechnology company still on NASDAQ, but never mind. It was a good attempt, and probably as a result of that, I got knighted by the Queen in the year 2000, and then eventually came to Singapore. So I'll talk about this story a bit, and then I'll talk about, what is creativity and what is the process by which we can make progress in science. So this is the Singapore part of my journey. When I came here, there were just sort of a prison, actually, on the site of the Biopolis. I don't know if you know the One North site. Some of you probably do. It's near the Ministry of Education, Buona Vista. But some of the buildings that we work in now were formerly a prison. And Philip Yeo joked to me when he came. He said, "Well, if you don't work hard enough, that's where you'll be." But what's been amazing in Singapore has been this investment in science, in life science, and in physical sciences, and the cluster of buildings that's developed around the One North site. I currently work in a building called Neuros and Immunos, which is just in the bottom corner. But when I first came, that building Proteos was just being assembled. And it's an amazing investment by the Singapore government and by the Singapore people in science, and has been incredibly exciting to be part of. And it's still growing. So we started a drug discovery unit, the Experimental Therapeutics Center, 10 years ago now. I started that, and it's now run by a man called Alex Matter. And as many of you will know from reading the newspaper, the first few entirely developed, entirely discovered drugs in Singapore are now in clinical trial for the treatment of cancer patients. So it's been an amazing journey. So where do you start your journey? Well, you always start your journey with your family, and this is a picture of me in the middle, surrounded by my family. I'm one of 5. My father died when I was only 19 from cancer, and that had a big effect on our family, though my mother was amazingly resilient and managed to bring us all up in those circumstances. And it was a Catholic family. I was joking over lunch that I didn't speak to a person who wasn't Catholic till I was 18, because we lived in the UK, but it was a very focal community. Primary school, secondary school, all within that community. And in those days, we were taught that people who weren't Catholics were certainly not destined for heaven, so not good people to talk to. But fortunately, the world's become a little bit more open-minded after that. I include the second photograph because the first photograph was taken by my sister, and my sister's now visible in the second photograph. I can't overemphasize the impact of the family environment we had. It was a wonderful, warm family. We all, as brothers and sisters, got on very well. Our parents were very understanding. Neither of them had gone to university. The idea that we would go to university was quite foreign to them, but nevertheless, we managed to do it. My father assumed that I wouldn't be there for very long and sent me sort of encouraging notes like that he could offer me a job if I wanted to get a real job. And I think my mother never really thought that I ever got a job because I stayed in the university for a long time. And so, but you know, it was a change in society happening all around us in those days, and still is today. So this is the man who probably had most influence on me. When I went to university college, it was hard to describe. We talk about curiosity and creativity. It was such an amazing experience for me to go to university in London. I left home. I left my entirely Catholic background. I went into a hall of residence and I shared it with a young man from Birmingham. It's the north of England, had a very strong regional accent. He'd come from a very working class family. He was a fervent Marxist, didn't believe in God at all, and you know, he exposed me to a very different view. And then when I went into the lectures, I loved it because I didn't have to go. I hate being told what to do by people. My wife can tell you that in great detail. So I really like to do what I want to do. And so university allowed me to do that. And I suddenly found that because I had that interest, now I was able to do well. Before I hadn't had the interest, and so I couldn't do well. And in my second year at university, I met this man, Alfred Mitchison, who's a very famous British immunologist. And he was amazingly challenging. He would get us all in the class to read a scientific paper and then tell us what was in it. And up to that time, all my teachers had been polite and said, oh, well, that's a good effort. And he would say, no, that's rubbish. You haven't understood it at all. Can't you do better than that? And this really turned on the lights for me. And I remember studying very, very hard so that I could give a talk that would be impressive to Mr. Mitchison, Professor Mitchison. And then I, in the end, made that huge decision that we all make in our lives, which is to have the courage to go up to him and say, can I do a PhD with you? And he said, oh, I don't take students from my own university, it's a bad idea. And I said, no, please, And he said, oh, all right. And I realized that was sort of how he hired people, and it's something I've rather adopted. If somebody's got great enthusiasm, they'll come back to you. So it's not a bad idea to tell somebody who wants to come and work with you, no, and then see what happens. If they come back, then probably they're a good person to hire. So he really inspired me as a scientist, and was very fortunate that in his lab at the time there was a young American postdoc called Don Silver, and Don really rescued me because Mitchison's view of academic supervision was not very much. I mean, he gave me a paper and he said, oh, get on with it, And there was so at one level he was a very inspiring figure because he didn't constrain you in any way. On the other hand, it wasn't much direction. So I was very lucky to meet Don, and the two of us got on very well. And so within the first couple of years of my PhD, we wrote our first research paper together, and it was accepted immediately, something that's never ever happened to me since. So I've written about 350 scientific papers since then, but this is the only time that happened. And I still don't quite understand it, but it was a very encouraging start to my career. And then I left that lab and I went to work with Lionel Crawford, a virologist who was working in London at the Imperial Cancer Research Fund. He was a very different man. He and I didn't get on as well. He was very rigorous. Av was always about ideas. Lionel was about technology and making it work. But but it was a great environment to do experiments. And it was in his lab that we made this discovery of P53, which was published in 1979 and has a very boring sounding title, but that's what happens with most scientific papers. And really, this is it. This is my life. You know, some people say your whole life, Dave, is just a band on a gel, and it's sort of true. So the top one's called T antigen, and that's something that the virus makes that transforms cells. And the bottom one is called, rather boringly, 53 or P53, because it's 53,000 molecular weight, 53,000 times the size of a hydrogen atom. And that is the host protein that interacted with the virus and was our clue as to how viruses might, in these animal model systems or cell culture model systems, how they might cause cancer. And eventually, over many years, and really only in the 1990s did we fully understand this, we realized that these viruses were interacting with two cellular proteins, the P53 gene and the RB gene, and these proteins are very, very important proteins that make our cells remain normal. I christened P53 guardian of the genome because it helps our cells not to be damaged by radiation or other signals, and keeps our genetic material secure and safe. And so this discovery that these viruses would interact with these proteins really told us a lot about human cancer, and it's continued to be a fascinating area. I think the stimulation that you get from your colleagues is terribly important for creativity, being part of a community. So if you see the great scientists who achieve an enormous amount, they're often embedded in fantastic institutions, surrounded by other very creative people. And I was very fortunate to go to Cold Spring Harbor when I had finished my postdoc with Lionel. In fact, the paper on P53 was written sort of mid-Atlantic because I was shuffling between the two places at the time. And when I went to Cold Spring Harbor, it was this contrast between Great Britain and America. I mean, now things are more homogeneous, but in those days, people in Britain were still polite to each other. You know, we went to the pub in the evening, and that's kind of life. And I went to Cold Spring Harbor, and it was just like chaos. Everybody was very rude. They were competing like crazy. They all appeared to be your best friend immediately, but then you realize they weren't. I mean, to make friends in Britain takes about 10 years. To make friends in America takes somewhere between a week and 10 years. I mean, but superficially you seem to be. So it was very exciting, and surrounded by colleagues, because Jim Watson was the discoverer of DNA, people flocked to this laboratory to be in his orbit, if you like, and so we had fantastic science, and it was a great environment. And we started to use this new technique, which is the development of antibodies. So we were able to make these reagents in tissue culture in very pure form, and it was a very exciting time. And then I went back to Imperial College and started to teach. So I taught immunology. And I must say, teaching, if you want to learn something, there's no doubt that teaching it is the best way to learn. And many of my students that I taught are still scientists, and they come and see me and make me worried about how old I am, because they look pretty old now, and so something's going on that's not good. But anyway, it was great, and we had a wonderful time. It was very unstructured. When I look back, the guy who had been teaching immunology before me left, and they just said, "Oh, David, you're in charge of immunology, teach immunology." That was the guidance I was given. So then I had final year undergraduate's immunology course. I designed the course, I taught the course, I examined the course. It seemed fine. That was okay. Nowadays, you'd have to have lots of teaching quality assessment, and everything would be checked very carefully, but in those days it was different. And I had wonderful colleagues. So there were 4 of us, young people, appointed as lecturers to Imperial College. You know, we all got on incredibly well. We were kind of the young ones against the old guard, and we were using all these new methods of molecular biology, of protein chemistry. And we christened ourselves the Gang of 4. Some of you older ones in the audience will know what that's about. And we all did very well. And it's sort of interesting. I was reflecting on it as I came over here that, you know, all 4 of us eventually got elected to be Fellows of the Royal Society, which is the kind of highest scientific thing that can happen to you within Britain. And And yet we didn't compete with each other. We really worked together. You know, we had this common desire to kind of bring these new methods to the United Kingdom. Most of them had been invented in the United States, and to really sort of build science in that system, and it was fantastic. I mean, the other thing that sort of taught me about creativity is my own children. So this is my son, Oliver, and my daughter, Amelia. Amelia is a cell biologist. Oliver is an engineer. And we have very intense family conversations about the future and science, and they've clearly got the bug. And, you know, you ask yourself, what is it that helps people to become creative? And I think it's definitely a lack of restriction. You know, not telling people, I'm going to come back to this theme, not telling people what to do, allowing people to have freedom to think and to be creative is very important. So the, you know, very rigorous exam systems that you love in Singapore seem to me not ideal for that process. So, you know, it's somehow we have to back off, was a phrase we heard over lunch, which I rather like. But I mean, somehow it's a balance. I mean, you must acquire knowledge, because without knowledge you can't think straight, and you need to acquire the process of understanding how to approach a problem, the scientific method of logic. But then at some other point, you've got to let your mind go free, because you want to think thoughts that nobody's ever thought before. You want to make connections that nobody's ever made before, and you want to question what is given before. So if you look at a textbook from the 1930s on biochemistry, the entire textbook's wrong. And we have to make the kind of assumption, I mean, that's a slight exaggeration, but it's not far from the truth. So we have to make the same assumption at some level, always, that knowledge has a degree of certainty, and then it has a degree of doubt. And the doubt is the interesting part that you have to try and push, but you can't throw away what's there that's right. So it's a kind of balance. So if we think about Newton and Einstein, it's a very good example. I mean, Newton's good enough for an Airbus to fly satisfactorily, no problem. It's just not quite good enough to get to Mars. You know, it's just a little bit out. So we mustn't throw away Newton, but actually Newton is nearly right, but Einstein's actually correctly right. So in the terms, the degree of precision is there. So we have to think, you know, hard about how we develop knowledge. We mustn't throw away the past, but we must build on it. And that's why libraries are so important, because we have to keep very close to us the knowledge we have and not lose it. In fact, every generation has to acquire the knowledge that we had in the past. It's a very important process. It's something that we kind of, I think, tacitly assume will happen, but actually requires a lot of people to put in a lot of effort. All you young people in the room are having to learn a lot of stuff, and you need to do that in order to keep human knowledge viable and functional. So the process of how we teach and how we learn is actually very, very important. So this is the book that I wrote, and I think writing a book was a tremendous challenge. I mean, as a scientist, you write papers. So a scientific paper will be maybe 3 or 4 pages. It'll be very structured in what you write. It's just an account of your experiment and your conclusion. And this is a book, so I had to start sort of from the whole process and think through it all. I found it very, very fascinating. I spent a lot of time in the library researching for this book, because what it is actually a collection of techniques, of methods of how to do something. And it tells people the whole process of how to do something. And some of the nice letters that Ed Harlow and I got, well, the best letters were for people in rural universities who said they'd used our book and they'd been able to do the whole thing and it had worked, you know, which is a very satisfying thing. But it's a very different process, and I'm struggling to write another book at the moment, so it's not easy to write a book, I can tell you. So at Dundee University, when I moved from Clare Hall, that's when I started to have a bigger lab, and when I started the biotechnology company, Cyclocell. But it also was another time when something very formative happened in my life, and this was actually a phrase. So I was asked by Nature to write a short commentary on somebody else's publication, something called News and Views. And I had a very boring title for it, which is something like 2 proteins come together. And they called me up and said, David, that's the most terrible, boring title I've ever heard. Can't you think of something better? So maybe I went back to my religious upbringing, but I came up with P53, the guardian of the genome. And I titled the piece that. That piece has now been cited 5,000 times. I don't think anybody reads it, but I think, everybody who works on P53 loves it because their protein's the guardian of the genome. You work on some other, RAS or MYC or something, not very important, but ours is the guardian of the genome. And it's been kind of an interesting area of science, socially as well as scientifically. The people who worked on this molecule at the beginning still work on it. In fact, all of them are coming to Singapore on the 5th to the 8th of July because we're hosting the P53 workshop here. And 200 scientists will come to Singapore to talk about this one protein for 5 days. And they're very passionate about it, of course. And in that group of people will be the 10 people who were at the first meeting we ever held on this protein, which was held in 1982. So it's a very interesting process. I think one of the reasons that's worked is because the people in the field kind of like to work with each other, and there's a very cooperative environment, which is important. In science, you have to balance this desire for individual fame and recognition, which is necessary to some extent for career progression, which professor gets promoted, versus the need for people to work together, because you're actually trying to solve the problems of the world and the universe, and that needs you to cooperate. So it's always a tension. And in this field, I think that tension's been managed rather well, so that people are able to collaborate quite well and still interact with each other in a way that's still demanding and not accepting of delivered truth. So I'm going to talk now about creativity and sort of move on to the next section of the talk. And I had another picture of a 4-year-old, but I thought, well, never mind, we'll just stick with the same picture. So the average 4-year-old asks 477 questions a day. I have no idea if that's true, but it's probably sort of right, and it's interesting. Those of us who've had children know what I'm talking about. I mean, I used to love my daughter's questions, and we used to drive her to school, and she would ask a question, And so one of her questions was, "Dad, what's beyond the edge of the universe?" And there'd be a sort of pause in the car, and then my wife would start, and she said, "Mum, I don't want one of your long, complicated answers. I just want to know, yes or no." So, but curiosity is very important, and children have it. And I think, this is quite nice. I think the creative adult is the child who survived. And I think there's something in that. It's nothing to be ashamed of to ask questions. It's nothing to be concerned about, to constantly question why things are like they are. I mean, I heard this fantastic lecture the other day, which I hadn't thought about. Why are planets round and asteroids kind of like lumpy potatoes? And it turns out there's a completely precise mathematical answer to that question, and it's to do with the mass of the object. So as the object gets bigger and bigger and has a larger and larger mass, the force of gravity becomes so important that it makes the object round. So I had no idea that was true, but isn't that fascinating? And what was even more impressive was the guy on the program just went off and did the maths to show it was true. So clearly I can't do that, and probably somebody in the audience can, but not all of us. But it's very impressive to realize these questions that are very sort of obvious are out there, and we don't ask them. And I think somehow, thinking every day, you should probably wake up and think of 5 great questions. And this is, I think, a hero to many, many of us in science, because Richard Feynman kind of epitomized this process of thinking outside the box, and it was a very flamboyant and interesting character. I mean, his other enthusiasms were bongo drums and strippers and various other things, and he flew to remote places because he thought they just had very interesting names. But he was one of the most brilliant physicists in the world ever. And he said, "Study hard what interests you in the most undisciplined, irreverent, and original manner possible." That's a very interesting statement, because he wants you to study hard, but he doesn't want you to be constrained by too much by what other people have thought. He wants you to question everything, and questioning is very critical to the creative process. I like some of these quotes as well. I mean, this is a nice one. I think people always worry about wasting, using things up, and this is good. You can't use up creativity. The more you use, the more you have. And learn the rules like a pro so you can break them like an artist, from Picasso. And the chief enemy of creativity is good sense, also Picasso. Picasso's a bit of a hero of mine, because I just think the creativity that he had is extraordinary. And here's an example. So here's a painting by Picasso of three women. It's a very, very beautiful painting, but it's relatively figurative. And the next year, he painted that, which is so amazing. I mean, it's another very beautiful picture of a woman looking in a mirror, but it's extremely different. And you realize the depth of his creativity, that he could do those two things. And if you look at this picture, I mean, in terms of classic skill as a painter, it's very, very, very good. And this painting is very, very, very modern. And, you know, it's not obvious in the same way of the technical skill that's there. So I think, you know, he's a very good example of somebody who has this enormous ability to challenge and change. If you look at his career, one day he's working in ceramics, the other day he's painting, the next day he's doing sculpture. I mean, he's doing other things as well, but he's a very, very busy man. So linked to this is innovation and disruption. So innovation is something that we need desperately. We always need to try and improve things, but it's disruptive as well, because it kind of upsets people. So if you're Kodak and you're making film and somebody comes along with a digital camera, it's jolly upsetting because your whole business model has gone overnight. And there are many, many other examples. In fact, we're in the middle of that process in a dramatic way now with almost everything to do with retail because of Amazon. So these are very important ideas. So I want to talk a little bit about science and sort of a bit about the threats to science, as well as to help people to understand the positive things of science. So one of my anxieties, and it's probably not true in this audience because you've all come here on a Saturday afternoon to hear me, but in society as a whole, I have an anxiety that people don't understand how important science is and to distinguish good science from bad science. And so I want to talk a little bit about that now. So good science works. I mean, if you think about the things that science has given us, it's extraordinary. Clean water, sewage systems, agriculture, antibiotics, vaccines, computers, pacemakers, spacecraft, everything that we have. And the consequence of those innovations has been a tremendous effect on humanity, on our lifespan and our quality of life. So this is a graph of life expectancy, and you can see that basically nothing happened. All of us would be dead in this room except those under 25. Hands up, who's over 25? Yeah, quite a lot of us. So we wouldn't be here if it wasn't for science. And it all happened pretty recently. So you look here, it's sort of the 15th, 16th, 17th century, that kind of time. And what's happened now is even more dramatic and is going on. I mean, this is since 1950. And you can see we've gone from an average world life expectancy of 45 to over 65 in a very short period of time. And this is the effect of scientific understanding. This is the effect of clean water, the germ theory, antibiotics, vaccines, all of the things that science has brought to us. And it's a huge effect on humanity. And hidden under this is the removal of enormous suffering, because people died in pain. If you read the kings of medieval times, and most of them were in agony most of the time after their 30th birthday, because they all had absolutely appalling toothache and goodness knows what else, and just absolutely a terrible life. So things have really improved dramatically as a result of science. And it's going on still. So this is HIV, and I don't think many people realize how narrow a window there was in technology and development with HIV. So we have the development of transatlantic aircraft after the Second World War, and we have the emergence of this terrible plague. And every single piece of science that we knew as molecular biologists and cell biologists was necessary to understand this virus, to isolate it, to develop the drugs that treat it, so that now a person who's treated with the right drugs has the same life expectancy as somebody who doesn't. And yet you can see what was happening in America. The number of AIDS deaths was just going up at a tremendous curve until these drugs came available in the mid-90s. And then the prevalence is still going up, but the deaths are going down. So sometimes when I read the newspapers and they sort of say, oh, I'm a bit worried about science, or didn't scientists cause HIV, or sort of silly stories like that, I get wildly angry, because actually the world needs to realize how narrow this was, this margin. If there'd been a bit more restriction on the development of molecular biology and jet engines had gone a bit better, this very tight relationship would have been broken. So it's very important that as society we understand science, that we're careful with science, that we nurture science. If we don't have a generation of new people willing and excited and supported by their families to be scientists and recognized as great people in the world because they're scientists, we're in trouble. So it's a very important profession that I sometimes feel is not very good at selling itself, and we need to do better. The rate of technology change in science is extraordinary, and this is DNA sequencing and the cost of sequencing. So soon, I don't know whether it will be 5 years from now, but it will certainly happen. Everybody will have their DNA sequenced as part of their standard healthcare, probably at birth, maybe later. And already this is going to have a huge effect on people's health. It's going to be one of those great uplifts, again, because we'll be able to tell what things people are likely to develop in old age and how we can help them to not do that. And we already see it, for example, with some of the cancer genes. We're able to greatly prolong the life of people who have a risk gene because we have this information. So I think we need to appreciate very much these kinds of issues. So one of the big challenges for all of us is knowing what the truth is. So we have an enormous amount of information. As a scientist, I'm constantly confronted by the work from my colleagues, which I doubt greatly, because it's challenging my work, so I have to examine it in great detail. But I have the information to do that because the way my colleagues publish their work is highly scrutinized, checkable, relatable, and I can call them up and say, hey, hang on, what's going on? But for most of us, this is a real problem. How do we know if things are true? That we're bombarded with information, and how do we sort out what's right from what's wrong? And how do we find things out? We used to go to libraries like this one and read books written by very learned people. But now we might go to Wikipedia, that's not so bad, or even worse, we might go to social media, which is getting more difficult, or we might listen to a certain man who tweets a lot, which is very bad. So the issues are very pertinent for us now, and I think we have to think very deeply about how we can educate ourselves to begin to recognize truth from non-truth. What are the tools we can use? What are the processes we can use? And one of the hardest things to do is to realize that what we call common sense, what is our natural human instinct, is not always correct. And that's quite difficult to get your head around. And it needs the process of education, a little bit of understanding of sums, a little bit of understanding of visual images and how they can be manipulated, just to get a sense so that we're more analytical. We should be like detectives, all of us, kind of trying to find out how that advertisement's trying to deceive us, or how that news story is not necessarily telling us the right thing. We need to be very kind of alert to these issues. I mean, in my own sphere, when we worked on P53, it was just beginning of the time when the link between tobacco and smoking had been established, but the molecular mechanism, how the tobacco caused the cancer, was not clear. And what we found with P53 was that the types of mutation in lung cancer smokers in the gene were exactly the type of mutation caused by the chemicals in tobacco smoke. So we had this extra link. And the tobacco industry were not very happy about this. In fact, they sent a bunch of lawyers to see me to sort of try and persuade me not to say that. So you have to realize that there's people in the world who want you to believe things because of their particular desire to get a particular message across. The tobacco companies wanted to make people think it wasn't that dangerous to smoke. That was in their interest to do so. So one has to be very careful as to how one approaches these issues of knowledge and risk and understanding how to find things out. So one way to do this is to teach. And I think teaching is very powerful. If you're teaching somebody else, there's a kind of innate responsibility in the process. You don't want to teach them something that's wrong. You want to examine how you're telling them the story. And And I use this in two ways. I used to always, when I gave a talk like this, talk about the Vietnamese boat children, because I love this story. So the story that I was told and read about and was reported widely was that the Vietnamese boat children, when they came to America, did very well in school. And even though they were going to rather bad schools and schools with not very good academic records, they all did very well. And so there was a study, and the answer to this study was, well, the reason they're doing very well is every night they go home and their parents want to learn every lesson that the children learnt at school. So they could learn the English the children learnt at school, the cultural things they learnt at school, the mathematics. So that was a very attractive idea. And I still like it so much that it's nice to tell the story. But more recently, I went back and discussed it with some people. Apparently, it's not so clear. The data is not as strong as we thought. But nevertheless, I think the idea that teaching is the best way to learn is a very important concept. But everybody in this room is a teacher. You're always teaching other people. If you think about it, when you're sharing an opinion with somebody else, you're teaching them. So are you teaching them the right things? Have you really thought about that opinion that you're offering? Whether it be something to do with the behavior of somebody else or what something's happening. So always, if you think about yourself as a teacher, it's a good way to think. So when we come to science, of course, we get into more difficult areas. So what science should we do? And what's good science and what's bad science? So actually, this is a moral judgment, but it's not the one I want to make. So this is good science and bad science as viewed for the kind of things we should do. But what I'm going to talk about is the fact that you could do wonderful, very, very good science in space-based reference research, and you could do very bad science in life-saving embryonic stem cell research if you didn't follow the correct principles of science. So the most important thing about science is the scientific method, how we do science. And the key feature of science is honesty. Very simple, absolute human quality. Science has to be honest. And if it's not honest, it's not science. And honesty means honesty. That is, you say the truth as you know it, as you can report it, as you can document it. So the problem with not doing that is the disastrous effects. So here we have this book by Ben Goldacre. If any of you, I'm sure it's in the library here. If it isn't, I know they'll buy a copy immediately, probably 10 copies. Probably everybody should read this book. It's a really good account of the scientific method and what goes wrong. And bad science, unlike good science, which has achieved all those wonderful things I told you, bad science doesn't do anything. Actually, it does worse. So, as many of you will probably know, the whole fantasy about the MMR vaccine being dangerous was propagated by one corrupt scientist who was paid by the Vaccine Defense League and lied. His paper was published in Lancet. It was withdrawn some years later. He went through the normal processes, but he's still teaching this, and a lot of people sort of believe it. It's absolutely false. It's completely wrong. It's been shown to be completely wrong time and time and time again. And yet the president of the largest country in the free world has recently tweeted that he's a bit worried about vaccines. I mean, so this, to me as a scientist, this is a catastrophe. And I kind of rant and rave about it. But the question is, actually, how do we solve this problem? This problem of misinformation that's going to affect people's lives. So there are measles outbreaks in America, there are mumps outbreaks in Britain. Children are getting badly affected by something where we have the perfect and completely safe answer to this problem. So we as a public, and I'm going to switch now from being a scientist to being somebody, an ordinary person, I mean, we are bombarded constantly with nonsense in the media. I mean, terrible nonsense. And one thing that you have to kind of develop is a nonsense meter, so you can kind of work out what's nonsense, what's not nonsense. So the sort of things we get are spurious correlations, which I'll talk about in a minute, common sense versus statistics, and then things like nutrition supplements, detox bars, and new age health cures, all of which we could discuss in more detail. So spurious correlations are really, really dangerous. So this shows the perfect correlation between the increase in autism and the consumption of organic vegetables. So the implication of this is the more organic vegetables people eat, the more children have autism. Look. P equals 0 to 9. But that's a correlation. It's not causality. It's two events coincide, but doesn't mean they're in any way related. I can give you an explanation for this if you would like. But would you like? Yeah, I suppose so. So basically what's happened is people start to eat a lot more organic vegetables. That's good. And then autism is increased because the criteria by which people diagnose a child as having autism have changed radically. So more children are diagnosed with autism because the definition of what autism is has changed clinically. So the two things go up. It's pretty interesting they go up, but you know, okay. So watch out for these things, very dangerous. And here's a whole lot, right? I mean, so when I was at Cancer Research UK, we became so concerned by the stories that appeared in the media about cancer that we have a kind of myth-buster website now. So everybody can go to this, it's free, and you can get answers to all of these lovely things like cancer is a fungus and sodium bicarbonate is a cure. That was popular. There's a miracle cure and big pharma companies are suppressing it. Cancer treatment kills more than it cures. Sharks don't get cancer. Cancer is a man-made modern disease. You know, all of these things, they're all completely bullshit and wrong. And you know, you can find out why they're wrong here. So, but I think we need more of this. You know, people need to know where they can go to get alternate information. I hope you can read this. This is a lovely cartoon, and actually we had lunch with the previous speaker, and he more or less talked about a man who had this property. So what it says here, wow, you have 3 master's degrees and a PhD. Yes, it's all very impressive, says the interview candidate. But interestingly, I have no common sense whatsoever. And then the interviewer replies, that's not the sort of thing you should say during a job interview. And the interviewee says, I don't see why not. So here's a little bit of stuff for us to do. You know, sorry about this, but it always gets, you know, it has to be a bit of. So 25 dots, A, B, C, D, which are random. Which is the random pattern? Don't tell me. Don't tell me. Okay. And you could say, David, why are you boring me with this? It doesn't matter, you know. It doesn't matter at all. But here's those information put a different way. This is the geographic distribution of cases of childhood cancer in different cities in the United Kingdom. Now it matters because, I live in this part of Manchester. In Manchester, therefore, in this part that I live, some dangerous virus that causes childhood cancer, some nasty pollutant chemical, therefore I must go to my MP and complain. I must regulate British science and British affairs much more carefully to avoid these things happening, and blah-de-blah-de-blah, lots of newspaper articles. But in fact, no, that's the random pattern. The random patterns always have clusters in them. If you think about it a lot on the way home, on the MRT, you'll work it out. It's just very hard to make, you see, this is very unlikely. Very unlikely. There's a lot of nice illustrations about this which you can look up. So the number of people who have the same birthday in a room is much, much more free. I'm not going to do it because I always do it the wrong way around. But anyway, you could go and talk over tea. But I mean, it's basically these events. There's a common sense answer, like, 365 days in the year, so 365 people. You have to have 366 people before 2 people have the same birthday. But no, it's something like 30 actually. So you know, our brains are designed to work in one way, but they don't always tell us the truth. So we have to put a bit of effort in to get to the right answer. This is another problem. So this is verbal logic. So what we don't realize very often in life is that we're making decisions on the basis of verbal logic. And it's very important. I'm a biologist. I'm useless at maths. Well, I can do a little bit, but I'm not great. But what I actually do when I go to work is verbal logic. I discuss my results with my colleagues. We discuss the answer. We deduce. We use logic to deduce. And words are very, very important. So here's something silly, right? Men live on Earth. Earth is a planet. Mars is a planet. Therefore, men live on Mars. Sounds ridiculous. But look at this one with my students, right? Oh, it's gone away again. Anyway, I'm going to do it because it's probably... Actually, yeah, sorry about this. I should have checked. I did check them, but somehow these new problems didn't appear. But anyway, let's see. I don't know if you can help me just move that graphic away. This one. See. Okay, sorry. Yeah. Oh yeah, there it is. Okay. Oh no, I thought we can just delete it.
Yeah, I think it deleted it.
Okay, no, good. Okay, now we can go back to this presentation. Yeah. Okay. Okay. So I had a diagram. I apologize. Things go wrong. Life's like that. But this is now putting the same statement about the planets, but into a very scientific kind of discussion that I might have with one of my colleagues. So it says MDM2 is phosphorylated by ATM. Phosphorylation of MDM2 by ATM controls its activity. P53 is phosphorylated by ATM. Therefore, P53 is controlled by ATM phosphorylation. That sounds very intelligent and smart, and it's probably true, but it's the same logical flaw. There's no proof, no causality, no link. And so this is one thing that I think we have to be very careful of. So when you read things, be very aware of people making associations and correlations that are not justified. And I think it's sort of fun to do that. And Straits Times actually isn't too bad, but some other papers we won't discuss. So now I'm going to give away all my secrets, because we're nearly at the end, and tell you how to do this, which is good. So, I mean, I think if you want to think great thoughts, you have to ask a good question. That's not a small thing, so think hard. I mean, I think the thing about the planets being round and the asteroids being lumpy is a good question. That's sort of very absolutely true, and there must be a reason, and you know, you might be able to work it out. Try and ask it in a different way. People have often asked me this: how do you discover things? And it's when you feel like you've made a discovery. I can't quite describe the process, but it's some sort of inversion. In other words, you try to look at it from upside down or in some other way. It's something that happens that you just try to ask the question another way. And I think it's something I try to practice. It's a lot to do with words. Just try and restate the conclusion in different words. See if it still makes sense or if there's a hole in the argument. You need to read all the time. That's why we're in the library. I can't tell you how many times things that have happened that I've discovered or done have come from just pulling information together. So you just have to read voraciously. And then have time. People, we rush around far too much these days. And, you know, just sit quietly and have a good think. Talk a lot. Well, I do that. That's a very big problem of mine. But it's also good to listen occasionally. So, you know, if you can find a colleague, I have one or two colleagues in Singapore, we just have coffee in the morning. And I'm sure the A-star senior administrators say, what's happening? David's sitting having coffee with a friend. Is that work? But actually it is work, because what we do is we talk about science and we think about it and we discuss it. So, you know, we have to have that, because otherwise you won't make the kind of progress you'd want to make. So what's going to happen next if all goes well? I mean, we face the most amazing prospect in science at the moment. From every aspect of science, the world could be a completely wonderful place. There's no doubt we have the capability and the resource to solve the world's problems. Whether it's energy, whether it's food, whether it's population, all of the solutions are available to us. And we just have to do the science, and society has to recognize and help and come along with the process. So, and we have to dream. This is the Babel fish. I think this would solve a lot of problems, actually. So one of the problems we have is we can't speak to each other. In Singapore, we're very familiar with this. It's called Singlish. So how do we actually communicate better? And we're beginning to get there. Voice recognition is improving enormously. The artificial intelligence approach to language recognition is improving. I think in a few years' time, you will be able to translate in real time between languages, and that I think would have a huge impact on the world and society. In the book, which is the Hitchhiker's Guide to the Galaxy, this actually is claimed to be one of the major causes of trouble, because once people understand each other, they start to fight more. But I don't think that's really true. This man, I think, is a very inspiring man, Mr. Musk, and he wants to go to Mars, and he wants to make all our cars electric, and he just seems to be able to do it. There's this energy that comes from people who follow this very, very rational scientific approach to development. And we are going to be able to do enormous things to improve our capability, whether it's to help disabled people to walk again using these exoskeletons, whether it's to understand human disease even more in detail. The last few years have seen incredible progress in the treatment of cancer using new methods. So we're just making great progress. And we have the possibility now to manipulate the genome, and I think not for people, but for other organisms, this is going to give us enormous potential. And yeah, it's working. Photoelectric cells are cheaper and better than we imagined. Mr. Musk is now selling a tile for your roof that he has guaranteed for infinity, or as long as your house is there, whichever is the earlier event. But I mean, it's still pretty amazing. So, very soon, if we don't lose faith, the benefits of science to society will go through another, I think, huge uplift. And we're beginning to get at biology in a way we couldn't before. Some people call it synthetic biology, but we're beginning to be able to use the knowledge we have to re-engineer these processes. And one thing that will happen is the ability to store information, which is, of course, vital in the age in which we live. So we probably will be able to store information in DNA. And you can see that currently the entire knowledge of the world could be stored in 1 kilogram, which is, I don't know what that is. What is that? It's probably 1/10 of a kilogram. So 10 of those, all the knowledge in the world, if it was encoded in DNA. There's a bit of a problem, how to write it, how to get it back, but it's not impossible. So the potential of these things is huge. And I think the risks are also there as well. So society has to progress in every direction. It can't just progress in the technical collection. It has to in the social and in the moral. It all has to progress together, because we don't really want to end up here. I don't know if any of you read this wonderful science fiction novel called Ready Player One, but basically it's a sort of dystopian future in which everybody's just playing computer games but not living their lives, and that's not something we want to go to. So I think it's very exciting to talk to you all, to, I hope, give you some of my enthusiasm for the future. I have great hope for the future and great hope for mankind. I think we can do all of these things, but we must keep ourselves alert, because there are difficulties out there with people who want to persuade us to think certain things. And the most important thing is not to do what people tell you to do, to think as an independent person. Thank you.